the Mojave Air and Spaceport in Southern California. At this secretive facility, an aeronautical revolution is occurring. Engineers are preparing to create history by flying a new aircraft for the very first time. Designed to lift a 240-ton payload to altitudes of over 29,000 feet. This new airplane has the potential to radically transform the future of aviation on Earth and in space. But first, it has to leave the ground.
The original design intent for this carrier aircraft or mothership was to carry 500,000 pounds, which to put in context is about 2.5 737s fully fueled.
It's more weight than has ever been lifted by an aircraft of this design. To achieve this goal, they've had to redefine aeronautical engineering and create an airplane unlike any other. Stratolaunch.
The Stratolaunch is in a league of its own in terms of airplanes. When it comes to just sheer size, wingspan, engines, fuselages, nothing can compare to Stratolaunch. It is the world's largest wingspan airplane, 385 feet wingspan. That is roughly the size if you took a Saturn V rocket from the Apollo days and laid it on its side. That's roughly the length of our wing.
Standing over 4 stories high and with a wingspan wider than a Boeing 747, Stratolaunch is the largest aircraft ever constructed. It's powered by 6 gigantic engines, each producing over 50,000 pounds of thrust. Its mission? To carry rockets and prototype aircraft to altitudes of over 29,000 feet before releasing them into the atmosphere or beyond.
Brakes now. Brakes are off.
But building the world's largest airplane presents some enormous engineering challenges for the team behind it. For a start, how do you ensure it's actually going to get off the ground?
So it is a big challenge to make an airplane this large and light enough to make sure it can do the job.
Then, once airborne, how does a 3-man crew maneuver something as wide as a football field is long?
Takeoff power set. All engines pulled.
The airplane's far too large for a human to be able to move the control surfaces while it's flying.
And how do you launch a payload into space?
Carrying a 500,000-pound payload to altitude is a huge challenge. Nobody's ever done it like this before.
Echo Zulu, Roger, runway 8, wind 120 at main.
Today will be the most significant moment in Stratolaunch's history. After 6 years of design and construction and months of taxi testing on the runway, pilot Evan Thomas is leading the 3-man crew about to take this gigantic aircraft into the sky for the very first time.
It's a little daunting. As a pilot, it is unusual, and it's hard to compare it to, in your mind, to something else that you've flown before, because really there's nothing like it in the world.
10, so 1.1.
With the eyes of the aviation world watching, failure is not an option.
Building an aircraft of this scale requires that our design and build teams have incredible attention to detail.
And it's not just the team's reputation on the line.
We are putting 3 human beings in the aircraft, and they need to come home and land safely.
Touch 5 super, runway 30, 110 at 6.
It's a mission no one takes lightly.
Even today, I walk in and I'm amazed by the size of it. The design capability of being able to carry 500,000 pounds, that's roughly equivalent to 2.5 fully loaded 737s. It is a huge amount of weight, and it is an order of magnitude above what any other airplane can do.
Lifting this much weight means that every part of Stratolaunch's airframe needs to be supersized, including its elevator control surfaces, the devices that enable the airplane to ascend and descend. By tilting the elevator up, the pilot changes the airflow over the wing and tail, causing the plane to climb, and vice versa.
In order to make the airplane pitch to climb or dive, we need enough control surface that will change the aerodynamics over the tail and move the tail, which then moves the rest of the airplane.
Measuring 29 by 6 feet, the 4 elevators are the largest control surfaces on Stratolaunch.
Our elevators are larger than you will find on most conventional aircraft simply because of the weight and the size of the airplane that we need to move.
But these supersized surfaces present a challenge in flight. The force of the air moving past them is too great for crew to manipulate the elevators by muscle power alone. So, can the solution to this unique challenge be found with the great innovators of the past? At the Evergreen Aviation and Space Museum in Oregon, pilot Mary Hsu is uncovering an airplane with a control system on a scale unlike any other. This is the Hughes H-4 Hercules.
Oh my gosh, the size of this is just incredible.
For over 70 years, it was the largest aircraft ever built.
It's hard to believe that this airplane would fly. It almost brings a tear to my eye just to look at it.
Standing the height of an 8-story building and weighing in at a whopping 250,000 pounds, the H-4's wings are so wide that the Statue of Liberty could lie across them. The brainchild of pilot, philanthropist, and film producer Howard Hughes. Due to wartime shortages of metal, the H-4 was built almost entirely from wood, a fact that earned it the nickname the Spruce Goose.
According to Howard Hughes' notes, this airplane was designed to carry 152,000 pounds of load. And to put that into perspective, up until that time, one of the big airplanes was considered to be the DC-3, and it would carry about 6,000 pounds. So no wonder people thought Howard Hughes was crazy.
Weighing almost 400,000 pounds fully loaded, it required engineers to think bigger than ever before. But much like the team behind Stratolaunch, Hughes encountered colossal challenges as he designed his record-breaking aircraft.
Oh my gosh, I'm going to sit where Howard Hughes sat. Isn't that amazing? Wow.
Until the H-4, airplanes were controlled by a series of cables connected to the pilot's control column.
Due to the sheer size of this airplane, conventional controls could not possibly work. So Hughes and his engineers had to come up with a new plan and develop the oil hydraulic pressure system.
As the pilot inputs a movement in the cockpit, cables signal pumps to direct hydraulic pressure to the relevant control surfaces, disrupting the airflow over them and changing the direction of the plane. This means that for each pound of pressure exerted on the controls, 1,500 pounds of pressure is directed to move the relevant surface.
These flight controls are very exciting because this is the first pressurized system for boosting those controls, which allow an airplane of this size to be flown. Now, smaller airplanes don't need that. We can use the cables, but this, because it's so huge, it would take the force of 200 men to be able to fly this airplane.
Although it was completed after the war ended, the Goose did fly. On November 2, 1947, observers witnessed Hughes take to the skies. It only flew for 1 mile, at an altitude of 69 feet, but it was enough to change aviation forever.
Hughes proved that big airplanes can fly, and it paved the way for all the big airplanes of the future.
And with Stratolaunch now poised to become the largest plane in history, the engineers behind it must look to Hughes's design to help them reach the sky. In Southern California, a monumental flying machine is preparing to take to the skies for the very first time. The Stratolaunch carrier aircraft. With a colossal wingspan of 385 feet and 6 engines, Stratolaunch is now the world's largest aircraft by wingspan, a record previously held by the H-4 for over 70 years.
I would like to think we are following on in the legacy of the engineering team and the builders of the H-4.
And the principles behind Hughes's pioneering control method are exactly what Evan and his team will need to get this 21st century behemoth airborne.
The Stratolaunch has control surfaces that are hydraulically powered, but they're mechanically signaled, which means we have cables running from the yoke up in the front cockpit all the way to all the different control surfaces. We said, well, rather than have a bunch of computers that would control the hydraulic system and display that information to the pilots like it's done on a modern airliner, we'd go back to the old 747 or Hercules H-4 days.
Despite the difference in design, some things remain the same even 70 years later. To get an airplane this size into the sky still primarily requires 2 things: lift and thrust.
It's the world's largest wingspan. Even the biggest 747 or Airbus, their wing stretches from our outer engine to the other outer engine. And we've got another 60 or 70 feet of wing on either end of that. So truly, in terms of wingspan, this is something that no one else matches.
Eclipsing the Spruce Goose by over 65 feet, Stratolaunch also dwarfs its predecessor in terms of power.
We can see the 3 engines here on the left wing. There are another 3 out on the right side. Those are Pratt & Whitney 4056 engines. They each produce 56,000 pounds of thrust.
With a wingspan longer than a football field and 6 massive jet engines producing more thrust than 10 fighter jets, Stratolaunch is poised to become the largest aircraft ever to take to the skies. It's a new milestone in aviation engineering. But the team still faces many obstacles.
No airplane has been ever designed before to carry this large of a payload in this configuration.
Adding a payload will make Stratolaunch one of the heaviest aircraft in the world. A fact that presents many challenges for senior design engineer Grace Wang.
Designing an airplane around that one large payload is really difficult. If it were a lot of smaller payloads split up, that'd be a lot easier. But just this one massive, massive payload, that's a big deal.
Lifting a payload this large in this configuration is a challenge never before faced by aircraft designers.
Some other examples of airplanes that have carried big payloads are the Antonov AN-225. It carried a payload just under 500,000 pounds. The modified 747s that were created to carry the space shuttle.
But cargo aircraft like the Antonov 225 have the luxury of storing their payload inside the plane. And although the NASA-modified 747s transported their vehicles outside the aircraft, the space shuttle weighs roughly 165,000 pounds, just a third of the weight Stratolaunch will transport.
The challenges of carrying one 500,000-pound enormous payload in one spot are that you have really high point loads. It's also really bad for the bending moment of your wing, and it's just a massive spatial problem.
To ensure Stratolaunch is capable of carrying the record-breaking payload, Grace and the team must find an airframe design capable of taking the strain. For inspiration, they must look to engineering breakthroughs of the past. Test pilot instructor Andy Edgell has come to the Valiant Air Command Warbird Museum in Florida to uncover the engineering solution to one of World War II's most difficult problems.
This is the XP-82 twin Mustang. Based on the original Mustang design, as we can see, it is two Mustangs strapped together.
Over 7 decades after its inception in the early 1940s, the XP-82 still remains one of the most unusual aircraft ever constructed.
She immediately reeks powerful, she immediately reeks damaging. She's an absolute beast of an aircraft.
The brainchild of American engineer Edgar Schmood, the XP-82 was designed as an escort fighter that could carry enough fuel to travel thousands of miles on long-range missions over the Pacific Ocean.
Now, the way the twin Mustang solved this problem was it's got an extended fuselage just aft of the cockpit. It was extended by about 5 feet, and that freed up space to put more fuel into the fuselage section. And remember, there's not just one fuselage on this aircraft, there are 2 fuselages. So already we're getting more fuel in the aircraft. Additionally, they filled the wings full of fuel and were able to put at least 2 drop tanks under each wing. And a drop tank is an external fuel tank. And once you've used up the fuel, you can jettison or drop the fuel tank.
But with the wings carrying additional fuel tanks, there was no room for the machine guns that the original P-51 Mustang had installed to defend its bombers against enemy fighters. An alternative solution was required.
So the beauty of the twin fuselage design aircraft is that it offers enormous versatility. Somehow you've got to strap the fuselages together, and they use this center wing section here. Now, this is an aerodynamic surface. It helps the aircraft fly. But in addition, it affords the engineers and the designers some extra space to put stuff. Now, here you can see they've decided to put 6 50 cal machine guns. Additionally, on this hard point here, they could hang an enormous 400-gallon fuel tank to extend the range even further.
With onboard fuel and drop tanks combined, the XP-82 could fly distances of over 2,400 miles, far outstripping a conventional P-51 Mustang. But the twin fuselage design was useful for more than just increasing fuel capacity. To demonstrate, Andy and pilot Ray Fowler are taking to the skies.
Let's check for everything. I think they got enough runway. You ready to do this?
I'm ready.
All right, let's do this.
Oh, that is loud.
It is amazing. And that's coming from someone who flies jets for a living. The other advantage of a twin fuselage and twin cockpit aircraft, it would allow the person in the left-hand cockpit to rest while the person in the right-hand cockpit took over control of the aircraft. I don't know anyone who could sleep through this racket.
Although World War II ended before the XP-82 went into full production, it was eventually reclassified as the F-82, and it saw service all the way up to the Korean War. Today, this is the only one in the world still flying. Back in California, engineers have taken the unique concept behind the XP-82's twin fuselage and supersized it. In the Mojave Desert, senior design engineer Grace Wang takes a rare moment to appreciate the mind-blowing scale of the unique Stratolaunch project.
I love actually getting on the airplane and getting your hands dirty. A lot of engineering companies, you don't get to do that. You don't see very many twin fuselage airplanes, and that's because the mission of most airplanes doesn't drive them to this design. So in our case, the mission happened to drive us to this corner. The payload goes underneath the center wing here. There's 5 attach points, and the max load that one single one of these points will take is over 600,000 pounds. And that's crazy. That's about the weight of a 777 just taken at one place.
Measuring 240 feet from nose to tail and situated 105 feet apart, Stratolaunch's twin fuselages are unparalleled in aviation history.
The fuselages are spaced apart how they are for a really big centerline payload and to provide clearance on the side for separation dynamics. But it's really nice in that it actually gives you some flexibility for smaller payloads. So instead of one large payload, you could put maybe 3 smaller ones in between these fuselage. When I look at this twin fuselage design, part of me as an engineer thinks, okay, this makes sense. And another part of the aviation fan in me just thinks, hey, this looks really cool.
The twin fuselage may be the perfect airframe design, but it also creates another problem that must be overcome.
We are here at the wing and fuselage intersection. We call this the wing to fuselage joint. There was a lot of effort put into this wing. So obviously it had to carry enormous load, in particular bending moment.
Measuring almost 330 feet long, Stratolaunch's wings are placed under immense strain. This is most prevalent in the center. The weight of the payload, combined with the lift generated in flight, creates what's known as a bending moment, a force that's trying to snap the plane in half.
So the amount of bending moment at the center of that wing, it's hard to count millions of hundreds, but we did, and it is 800 million inch-pounds. And you're like, well, what does that mean? So we put it in terms of elephants. So that moment is the same as if you had put an elephant, an African elephant, the big ones, on a ruler a mile away. So that's the bending moment that the center of that wing has to take, 1 elephant mile.
To overcome this vast force, the wing is constructed around 4 massive continuous spars that run from one end to the other, without stopping inside the fuselages.
These spars are massive. They weigh about 16,000 pounds each. And I think that is the largest single airplane component ever made.
But being so massive means that when something goes wrong inside the wing, there's only one way to fix it.
We need to go up in the wing routinely to repair parts or to fabricate parts. There's a lot of systems, flight control cables up in here and hydraulics. A lot of people had to spend a lot of time up here in these tiny bays. It's hard to get a sense of the scale of this airplane, but when you disappear into this hole, it kind of gives you a sense of how massive this airplane is and how much work it was to put together.
Stratolaunch is a milestone of engineering. But to ensure it's capable of dealing with the extreme forces of flight, engineers must overcome another complex challenge.
To find a design that worked, we had to create something new because there's not much precedent for anything like this. We were really starting from scratch.
And draw inspiration from the great innovators of the past.
Oh, I cannot wait to see this thing. Oh, wow.
The Stratolaunch carrier aircraft has redefined aviation. 100 miles of wiring, 28 wheels, and 6 engines have gone into creating an airplane of gigantic proportions. If it can get off the ground safely, it will become the largest plane ever to take to the sky. But before that can happen, the team must ensure that the airframe is strong enough to cope with the forces of flight, yet light enough to get off the ground.
When you're building an airplane, weight is central. Weight doesn't help. The whole lift equals weight equation, every pound that you can pull out of an airplane helps. This airplane also has to be really strong to support that elephant mile bending moment. Also, all the other plethora of loads that it's experiencing, the structure has to be incredibly strong. Strength and saving weight aren't really compatible in engineering usually. When you want to make something strong, you usually make it out of better material or you throw material at it. You make it bigger, you make it wider, you make it thicker. So saving weight and being strong are kind of two opposite objectives.
So, could the perfect, strong yet lightweight material be found in the innovations of the past? On the edge of Dallas, Texas, is a groundbreaking piece of aviation engineering that could offer the solution for the team at Stratolaunch.
Oh, I cannot wait to see this thing. Oh, there it is. Oh, wow. It's the Beechcraft Starship. What a unique looking aircraft.
Engineer Dan Dickrell has come to discover its secrets.
Look at the design of it. It's got two massive engines in the back, those wings that come out with the vertical wingtips, the swooping nose, the front forward-facing wing. This thing looks like nothing else. The shape of the Beechcraft Starship, however, is not the game-changing aspect of it. When it was built in the 1980s, something else entirely that really changed the game.
Designed by aviation pioneer Burt Rutan, the Starship was built to be the blueprint for the next generation of business aircraft.
So historically, airplanes were made of wood and fabric. Later on, materials like steel and aluminum were used. These were much stronger, but also actually ended up being much heavier. Now, when it came to the Starship, Rutan needed a solution that was just as strong as metal, but also a lot lighter.
By saving weight, Rutan could make the Starship more fuel efficient, setting his design apart from the competition. His solution was to use a material that was relatively untested in aviation at the time: carbon fiber. It was a choice that would create a revolutionary aircraft.
All right, so we're gonna take this aircraft up into the sky and see what it's capable of.
And here, flaps. And pull the power back so we don't overspeed.
Raj Narayanan is the proud owner of this piece of aviation history.
Now, do you get a sense of when you fly that you can tell it's made of carbon fiber, the fuselage and the wings?
You can tell you're in a composite airplane because it doesn't behave like a metal airplane with the way the composite structure, the stiffness of the composite structure. Most other airplanes built at the same time that were metal airplanes are not flying anymore because of corrosion and fatigue and reliability.
The Starship was a truly game-changing aircraft. Its unconventional design inspired other mass-produced carbon fiber planes, starting a trend in composite materials that would change aviation engineering forever. Back in California, Stratolaunch manufacturer Scaled Composites have taken the use of carbon fiber in aviation to another level. Stratolaunch is set to become the biggest aircraft to ever fly. And to ensure it safely gets off the ground, the team has turned to a lightweight but strong composite material, carbon fiber. David Eicher is their director of engineering.
Stratolaunch is the largest carbon fiber airplane in the world. The fuselages, the cabin, the tails, the control surfaces, the flaps, the ailerons, and the wing structure is all carbon fiber.
This means that without a payload attached, Stratolaunch weighs just 250 tons, about 375 tons less than a fully loaded Airbus A380. But for David and the team, carbon fiber does more than just save weight.
This piece, it's very lightweight. You can see it's very thin. It's extremely strong. So this piece maybe weighs a couple pounds at most, and I can easily stand on it. So I'm about 230 pounds. I'm standing on this piece that's just the skin and the ribs that are holding me up.
Despite the cutting-edge nature of carbon fiber, molding it into a section of airplane still requires work to be done by hand.
I'm gonna make a fuselage skin panel. And this is a way to make a really strong panel, but very lightweight. This is uncured carbon fiber.
David starts by layering sheets of carbon fiber on top of one another at 45-degree angles to give the piece strength in multiple directions. Next, he vacuum seals the part, bonding the layers together, before a lightweight honeycomb core material is added to provide stiffness and strength. David then adds the final layers of carbon fiber sheet, before giving it a final airtight compress.
So we're gonna take the whole thing, including the sheet at the bottom that's acting as our mold, and we're gonna stick it in the oven and bake it.
This baking process allows the epoxy to cure, joining the layers of carbon fiber into one solid part.
All right, so we've taken the part out of the oven and cleaned up the sides, trimmed it to the size it needs to be. And this is what the final part looks like here. You can see a nice smooth surface. And then here is the core. You can see the thickness that's been added. You can't tell the difference between the different layers unless you basically use a microscope. So it's all bonded very tightly together. It's extremely stiff and extremely strong. I could try to snap it, but I'm not going to be able to break it off like that.
It's a material that has revolutionized aviation and made Stratolaunch a reality. But now the time has come for the team to get this gigantic aircraft into the sky for the very first time.
10, so 1.1.
If they are successful, they will pass into the realms of aviation legend. Three crew members, 6 engines, 2 fuselages, the largest wing ever built. After 6 years of design, engineering, and construction, it all comes down to this moment.
Gosh, dude, get out of here.
We put the power up and pull back on the column. It's like an elevator ride going up.
Going up on 150.
The size of the aircraft does change the way we fly. We do things slow to get there faster, do gentle turns, no high bank maneuvers, no high G maneuvers. It is all slow and steady, wins the race. Flying this airplane is not like piloting a racing yacht. It's more like a supertanker. It's going the direction it is going, and in order to change that direction, you have to think ahead.
That touch slow, you gotta pitch down just a little. Engines look good.
After 149 minutes in the air, Evan and the crew line Stratolaunch up for the most nerve-wracking moment of the flight.
Touch
Super, runway 30, 110 at 6.
Now imagine I'm taking my supertanker at speed into the Panama Canal. You really have to do your lineup very carefully and then keep the ship as straight as possible coming into that target. For me, as the pilot, I'm most concerned about, will we be able to land it safely? That's the riskiest part of our first flight. What's going to happen when we touch down? Because we have to line up on the right side of the runway. You know the left fuselage is over there somewhere, but you don't know exactly where it is. It's very hard to imagine where it is. We only have 43 feet to either side before we're taking part of the airplane off of the runway. So it's quite a small window to fly this giant airplane into.
This difficult landing is all that stands between the Stratolaunch and its place in the history books as the largest aircraft to ever fly. Having successfully taken off and cruised the skies for over 2 hours, Stratolaunch is preparing for the most difficult part of its maiden flight, the landing. There is almost no margin for error.
Power's coming smoothly back.
At 500 feet, looking good, we're stable, we're on our line. 200 feet, still stable, still on our line.
Contact left, right.
Touchdown, we straighten the plane out on the runway, brake to a stop. For me personally, a highlight of my career of flying. Without a doubt.
Stratolaunch has done it. The team has solidified their place in aviation history. The world's largest aircraft, fully loaded, it weighs more than 6 blue whales, has a wingspan the length of 24 family cars, produces more thrust than 10 fighter jets, and can lift a 240-ton payload to altitudes of over 29,000 feet. Having gotten Stratolaunch airborne, the team has reached an aviation milestone.
Growing up, I did not have this concept of size, let alone this concept of size for a flying machine in my head. This is an incredible accomplishment.
Stratolaunch is one of the most ambitious projects in the last 2 decades of aviation. The courage and naivete that it took, whatever combination of that there was, and just the pure nerve to say, hey, we've never made anything this scale before, but we're gonna do it. That just still blows my mind.
It's a feat of engineering few thought possible.
I've been working on Stratolaunch for 7 years now, and it's a bit like my baby, and designing it, seeing it come to fruition, and seeing it fly.
By looking to great pioneers of the past for inspiration, adapting their ideas, refining their designs, and overcoming monumental challenges.
I never thought that I would work on an airplane this size. or of this complexity or this groundbreaking. Working on this airplane was kind of like winning the aerospace job lottery.